Thank you. I lost all that beginning part. That was such good stuff. Thanks. Sorry about that. Got to have a way to talk to me, so he doesn't have to come running over here. Sorry, I should have tested that. My bad. Oopsie. Well, it was all captured in chalk anyway. So capital L plus little l over 4. Okay? So is that a sensible way to think about where the center of this system is? Okay? Well, look what happens with this. Where's capital L over 4? Where's capital L over 4? Capital L over 4, and let me just draw this as a two-dimensional cube. Let's look at it right along, okay? So this is the x-axis, this is the z-axis, okay? And I'm going to look along the cube. Okay, this is L over 2. This is negative L over 2. So I'm not going to try to do a three-dimensional drawing. And here's that's where the center of the little cube is, and that's capital L plus little l over 2. And so what it's done is it's gone from, it said, OK, we're going to average this point and this point. So it's going to be capital L plus little l over 4, which is right over here, somewhere over there. OK? Now, why do I think that's the bad answer? Why is that a bad answer? Yes? The volume of the little cube is much smaller, so it doesn't actually incorporate any information about the shape, the amount of stuff that the little cube represents. Another way to say that, another way that I like it, to do it is, imagine you made the little cube really little, right? Let's imagine you made the little cube really little. Like, little l is like really, 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 like, it is really, 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 really little. Okay? Super small compared to big L. Well, in the limit that little l gets really, really small compared to big L, this thing looks like a lot like capital L over 4. In other words, it says the center of this big cube and this tiny little thing is over here. And you know that you're like, no, wait. I mean, if this thing is ridiculously little, in the limit that this goes to 0, I would expect the center to go back to the center of the cube. OK? And what's your name again? Emily. As Emily pointed out, the way I've defined this average does not incorporate anything about the size. OK? And so to make a consistent average, we have to incorporate something about the size. So now I'm going to incorporate the size. So bad answer, a better answer, a good answer, a good answer. By the way, I really think it's good to see why certain things fail. Right? Why does this fail as a calculation? Right? Consider the limit little l goes to 0. It's not intuitive. Okay? Now, let's see what happens when I put my good answer is going to be this. I'm going to weight the average by the volume of each object. Okay, so let's weight the average by the volume of each object. Okay? So the x center, okay, x center is going to equal, well, the x center of the big cube is always at 0, but I'm going to now multiply that 0 by the volume of the big. Okay? That's 0 meters times volume of big, which is meters cubed, plus the center of the little is always going to be at L plus little l over 2. And now I have to multiply by the volume of the little. And then I have to divide that by what? Well, this must be a length. So this is a length times a volume plus a length times a volume. I must divide it by the volume. The volume. Which volume? The total volume. So this is going to be V big plus V little. OK? Now let's see what this formula gives us. So x center is equal to capital L plus little l over 2. The volume of the little one is little l cubed, because it's a cube of side length little l. divided by volume of big, which is capital L cubed, plus volume of little, which is little l cubed. And if I can just write this out, this is going to be capital L plus little l times l cubed divided by 2 times capital L cubed plus little l cubed. So I claim that this is the formula for the volume, so the center of location of both of these cubes put together. Well, this is not the simplest formula in the world to see, so maybe we should think about it a little bit and see what we can do with it. Consider a limit, okay? What's the limit did I do over there that showed you that this one wasn't intuitive? I took the little l goes to 0 limit, okay? In the little l goes to 0 limit here, it's pretty obvious that in the little l goes to 0 limit, the numerator is going to go to 0. And for fixed capital L, little l goes to 0, the numerator goes to 0. This goes to x equals 0. So in the limit that this guy gets really, really little, that goes to 0. That's awesome. Let's think of another limit now. What if they were equal sizes? If big L equaled little l? Well, if big L equaled little l, so when little l equals big L, what do we have? X center is equal to, well, that's just going to be 2 big L, and that's going to be big L cubed. So this is going to be 2 big L to the 4th over 2 times big L cubed times 2, because there's 2 of them down here. Okay? Well, this is going to be L to the 4th over L cubed, which is L divided by 2. Ah, that's kind of cool. When they're equal sizes, their center is at L over 2, where they meet. Okay? And then you could take, by the way, let's take the other, well, we could take the other extreme, but I'm not going to take the other extreme. Let's not worry about the other extreme. Okay? So this gives you a sense of how you can consistently define an average or inconsistently define an average. But now when you see x times volume plus another x times volume divided volume plus volume, you say, oh my gosh, I can see where the integral comes into all of this. Because I did this for 2 cubes, but any domain that I can chop up into pieces, I can chop up into little cube-like pieces. And so now you just iterate on this example for multiple pieces. And what are you going to do? You're going to take the limit that those cubes go to 0 volume. That means you get more and more cubes. And so you'll have the integral in the numerator, and you'll have the integral in the denominator. And this is the process by which we define the x component of the centroid of an object. So this is the x component of the centroid. Okay? So just consider this and say, he did it for 2, big and little. He can just index them 1, 2, 3, find the center of each of those little cubes, add center times v plus center times v plus center times v through all of them, and then sum up all the v's. It could be 1,000, 1,000,000 in the limit that n goes to infinity. Okay? And that's how we define the centroid. So define. Define centroid is the geometric center. The geometric center of a region in Rn, in any dimensional space, But the n's that you care about really are 2 and 3. You really care about two-dimensional objects and three-dimensional objects. Because we write on two-dimensional objects, we draw on two-dimensional objects, and we live in 3 dimensions. So you're really going to consider n equals 2 or 3. Let x bar c, y bar c, z bar c be the location of the centroid okay? We define, so x bar c is the average x value. So remember, I've already defined the average of a function, right? The average of a function is the integral of a function over the domain divided by the integral of the number 1 with respect to the volume or area, whichever dimensions you're in. This is the integral of what function? It's the integral of a very simple function, x. It's the integral of x. It's just the integral of the x to the power of 1. Because x measures the x coordinate of any point. And therefore, when you're doing these little volumes, it measures a typical x coordinate of the volume. So it measures this thing, right? This is the x value. This is the x value. Here we've used the x center. This is, because of the definition of the integral, it's any x within a little piece of volume, but you're going to be taking the little pieces of volume goes to 0. So it really does go to the center. Right? They're really tiny. So this is equal to, in this case, the triple integral over the domain of the function x with respect to volume. And I've emphasized units, so you see that, well, this is length to the power of 4th. The most natural way to get length to the power of 1 is to divide by the volume. yc is equal to the triple integral of y with respect to the y bar c with respect to the volume divided by the triple integral over the same domain of the volume. And z bar c is equal to the triple integral of z dv divided by triple integral over the domain of dv. Now, the way this game tends to work when a prof gets on the board is, OK, let's figure out the center of a cube, right? So I have to do these integrals for the center of a cube. But that's kind of a painful integral. That's a really painful integral to do, right? Why is it painful? Because, well, it's just painful. We know where the center of a cube is, right? So maybe we can come up with a more interesting shape. Shall we try a more interesting shape? Let us try a more interesting. Yes? You tell me, does this relate to the average of a function? Yeah. So let's think of it this way. You can think of any general function, right? A general function is a bunch of numbers, so is a single number assigned at every point, okay? You can interpret that as, say, temperature. But now there's a particular function here that I'm averaging. I'm not averaging some general f of x. I'm averaging a particular function. This particular function measures a particular property. It measures the x component of where that point is. So yeah, it's related to the average, but it's a particular type of average. Okay? And that's what I want trying to emphasize. Okay? It's a very simple function to calculate. Okay? So I need a volume now. I'm going to do an example. Let's do an example. I want a volume that's non-trivial. Okay. Let's do this one. If I did a sphere centered on the origin, the x bar, the y bar, and the z bar are all going to be 0. Okay? I haven't showed that to you, but it's such a straightforward calculation that it's painful, and I can't bear to put you through that. Okay? But let's say we had half a sphere. Okay? So you made a Jell-O mold. Okay? Think of the Jell-O mold. It's half a sphere. Okay? And you want to know, where is the centroid of the Jell-O mold? Because this is crucial information for your Halloween party. So, e.g., upper 1/2 sphere of radius r. Radius r. Now, the first thing to point out to you is the denominator for each of these averages is the volume of the upper half sphere. Okay? So the volume, so you don't have to go through that right now, because I've chosen a sphere so we don't have to do those. So the volume is equal to, which is the denominator, is equal to 4 pi r cubed over 6. Right? 4/3 pi r cubed, but it's a half of that. Okay. Now, I draw the sphere because I'm so good at doing that. Yeah. So you look at it, and the first thing you should guess is that the centroid had better be in the sphere. Because the sphere is like this closed shape. Okay? But by the way, I want to point out to you, imagine donuts. Right? Imagine a donut. The centroid is not going to be in the donut. It's going to be in the hole of the donut. Okay? So never make a bet where you get to eat the centroid of the donut, because you will always lose that bet, even if you win. Okay? So it's got to be in the hemisphere. Okay? So that means this is going to be the upper half. It's going to be centered. This is going to be the origin here. Okay? So it's going to be somewhere in here. Now, let me say, I hope there's another intuition you have. The sphere is completely symmetric rotationally around the z-axis. So whatever calculation we do, intuitively we would expect that the x component of the centroid and the y component of the centroid are 0. Okay? That should come out of the calculation somehow. And then the z component of the centroid is going to better be non-zero. Okay? So let me just show you the x component of the centroid first. So now, the way I do this is the x component of the centroid times the volume. I'm just going to write it times the volume. So you know that I've multiplied through by volume for the time being, just because I don't want to carry a denominator. Okay? Is equal to the triple integral over the domain of the number x integrated with respect to something, with respect to something, and with respect to something else. Okay? So I am still of the opinion, if we could change the order of integration, all of that, but this is a really nice surface that there's clearly a z upper and a z lower. So let's do the z integration first. Okay? And then we can do the y or the x integration as we please. Okay? In fact, maybe what I'll do is I'll do the x integration first and then the y integration. Okay? And that might make life really easy. Okay? So z, I'm going to skip some steps now. We're going into second gear finally. I've been in first gear up till now. Let's go into second gear. Z lower is z equals 0. The plane z equals 0. Z upper, well, it's a sphere of radius r, and I have to solve for z. So z upper is r squared minus x squared plus y squared all to the power of 1/2, positive square root. Okay? That's because z squared plus x squared plus y squared equals r squared on the sphere. So that's that one. And then I have to have x min of y, x max of y, and then y min and y max. Okay? So I can do this integration with respect to z very quickly. This integration with respect to z is equal to this square root times x. So the integration with respect to z yields x bar c times the volume, which is the left-hand side, is equal to the integral from y min to y max, the integral from x min, which can be a function of y, to x max, which is also a function of y, pardon me, that the z integration, well, the x is constant with respect to z, and all I'm left with is r squared minus x squared plus y squared. then I have to do the x integration, and then I do the y integration. And now I hope you'll see why I chose the x integration next. Okay? I need to figure out x min and x max as a function of y. Well, after you do this integration, you look down on this hemisphere, and there's x, and there's the xy plane, and you see there's this curve, right? This curve, this circle, is the intersection of x squared plus y squared plus z squared equals r squared with z equals 0. Remember, I'm asking you to think of curves as the intersection of two surfaces. X squared plus y squared plus z squared equals r squared is the upper half hemisphere, or is this whole sphere, and z equals 0 is the z equals 0 plane. And when they intersect, you have x squared plus y squared equals r squared. That's obvious. I know that's obvious that this is the circle of radius r squared, but nonetheless, that's how you attain it consistently, by considering it as an intersection. Okay, this is x squared plus y squared equals r squared, and I need x min of y and x max of y. So x min, I have to solve this, is equal to r squared minus y squared, square root with a negative. And x max of y equals the square root with the positive. And so this is great. By the way, notice I still haven't figured out y min or y max because I'm a lazy person. And a lazy person waits until he absolutely has to do something in order to do it. And you will see that I absolutely don't have to do that right now. I'm just rewriting this whole integral, okay? There you go. You got to do two integrals. Now, one could have used polar coordinates here. Right? You could change to polar coordinates if you wanted. And you should say, oh, professor, this would have worked really nice in polar coordinates. Because I would have gone from little r minimum equals 0 to little r maximum equals capital R. So it's a nice region. And I would go theta from 0 to 2 pi. So I could totally have done this in polar coordinates. But I didn't want to throw too much into the mix. I didn't want to throw another change of variables here. The integral, what's the integral inside equal to? What's the value of the integral inside the parentheses? Think about it, think about it. Yes. Is it 0? It's not Jeopardy, man. Absolutely. 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 Yes, that is correct. That's 100% correct. I'm going to phrase it a little differently than you did, okay? It's good to know that an integral is 0, so you don't go through and compute it, right? And that's why I talked about symmetry and anti-symmetry. Everything inside the radical here is a symmetric function of x. That means if you go to fix at y, right? We're doing the x integral at a fixed y. R is fixed. Y is fixed. Everything inside the radical is a symmetric function of x. However, x itself is an anti-symmetric function of x. So evaluate this as x equals 1. It's something times 1. Evaluate at x equals -1. It's that same something times -1. That's what we mean by anti-symmetry. That's true for every x. The domain is symmetric. So when you integrate this, you're going to get positive numbers from x goes from 0 to the positive amount. And the same numbers, albeit negative, when x goes from 0 to the negative amount. And they'll cancel each other. Okay? In other words, this integral is 0. And so the whole result is 0. And so the whole numerator is 0. So xc is 0. That symmetry is a reflection of the fact that I have chosen to put this hemisphere centered on the x-axis. sorry, on the z-axis around x equals 0. I've centered it around x equals 0. Okay? If you need to convince yourself of that, you can convince yourself of that. Okay? Had you done this in polar coordinates, let's just go back and think about how this would have worked out in polar coordinates. Okay? In polar coordinates, in fact, I will do it in polar coordinates. I have that first integral up there. And if I were to choose not to do it in Cartesian, I would do it in polar. I let dx times dy, which is the area integration, that's equal to r dr d theta. Right? That's the area in Cartesian. That's the area in polar. In this case, then, x bar c, it's still x bar c. I'm still calculating. I'm using polar coordinates to calculate the Cartesian x component of the center of mass, sorry, of the centroid. The left-hand side is still that. Now I have to go from theta min to theta max. Well, theta min is 0. Theta max is equal to 2 pi, right? You're going around this whole disk. R min is 0, because you're right at the origin, and R max is capital R, the radius of the sphere, the radius of this disk. X is equal to R times the cosine of theta, and then inside the radical, I have r squared minus little r squared, and then I have to integrate that r dr d theta. So that's the same integral as the first line, except I've expressed it in polar coordinates. I can't change the left-hand side because I'm not doing anything. It's just two numbers, volume times the x component of the centroid. Okay? Now look at this integral. This has got an r stuff from 0 to some constant r. And then it's got a theta stuff. So just do the theta integral first. Change the order of integration, right? You can just swap the order of integration and do the theta integral first. Because this doesn't depend on theta, and this doesn't depend on r. Well, the theta integral is the integral of cosine theta from 0 to 2 pi. And that's 0. Because it goes up, comes back down, and goes back up, completely symmetrically. So this is 0 any way you slice it. Okay? You don't have to do those integrals. So the x component of the center of mass is 0. So the x component of the centroid is 0. The y component of the centroid will be 0 for the same reasons. Now I have to compute the z component of the centroid, okay? Which I hope you see is not going to be 0. So let's see where it lies. So the z component of the centroid is the same thing, but I have to integrate this with respect to z. Sorry, I have to integrate z with respect to volume. I apologize. I'm stumbling over myself a lot today. So I have to perform this integration. Now much remains the same here. I will stay in the center board because this is the one that's non-trivial. So much remains the same here. I can do that first integration. Z bar c, I'll put that a little higher up. Z bar c times the volume is equal to, well, now I have a non-trivial integral, the integral of z, which is not so hard. With respect to z, that's z squared over 2. So I'm going to put that over 2 out front. There's the 1/2. And then I'm going to just keep that double integral like this. And it's z squared over 2 evaluated at the upper bound minus at the lower bound. So I hope you see that the result is r squared minus x squared plus y squared. That's the result of the integration. Okay? Because it's z squared, and z squared is evaluated at a square root. And then I have to do the x integration and the y integration, et cetera, et cetera, et cetera, et cetera. I'm not filling in all the details right now. Well, I could do this, but I don't want to do this because it's over the disk, and I want to do it over the disk, and I want to recognize that, oh, polar coordinates make much more sense over the disk. So I'm going to switch this to polar coordinates right now. In polar coordinates, I have a 1/2. Again, it's the same transformation as I did there. It was the disk, so it's from 0 to 2 pi, 0 to capital R. Capital R squared remains. That's just the radius of that disk, minus x squared plus y squared is little r squared in polar. So this is little r squared. And this is the area element. And the area element in xy space turns over to r dr d theta, just as we did before. And notice the difference between that equation and this equation. Well, you got capital R squares minus little r squares, you got r's, you got all that kind of stuff. But the issue, the main difference is that's got a cosine theta. And that cosine theta integrates to 0 when you go from 0 to 2 pi. That doesn't have a cosine theta. Okay? So at that moment, you should pause and think, what if I had only done a quarter sphere? So I chopped it in half again. Then I wouldn't be integrating cosine theta from 0 to 2 pi. I would only be integrating it from 0 to pi, for example. Or an eighth of a sphere. Okay? So you could ask those questions. Like, oh, the fact that this vanishes because I'm integrating from 0 to 2 pi is because I've made such a symmetric domain. But I could do a quarter sphere or an eighth of a sphere, figure out where that centroid is. Okay? Now, I can do this integration. I'll do the theta integral first. The theta integral is going to give me 2 pi. So I'm going to have pi, because I'm going to divide that by 2. And I'm going to let u, I'm not going to do all that. I'm just going to do this integration. So this is going to be r dr of times r squared. So the r dr is going to be, that comes along for the ride, capital R squared. And little r dr is going to be little r squared over 2 minus, this is going to be r cubed dr, which is going to be r to the 4th over 4. I think I got that right. And I'm going to evaluate that at r equals 0 and r equals capital R. And I hope you notice that this is pi times capital R to the power of 4. 1/2 minus 1/4 is 1/4. That's a length to the power of 4, quite obviously. So where I have to divide that by the volume, the total volume. And so now I can see that my z component of my centroid, z component of the centroid, is equal to pi r to the 4th over 4 divided by 4 pi r cubed over 6. And I got to just do it. Well, the pi's cancel, and the powers of r cancel in a certain way. And what you're left with is 6/16, I think. Six sixteenths of r, which is 3/8 of r. So what does this tell you? It tells you that the centroid of any hemisphere is located 3/8 of the way up. Does that make sense to you? Well, if it was a slab, you would expect it to be like a kind of a rectangular slab, or a square slab, a cube. You would expect it to be located exactly at 1/2 the way up. Right? This is 3/8. That's very plausible. It's a little less than a half, because there's more stuff below that than there is above. And so that's why I like to keep units. That's why I like to keep a parameter in here, because you can always compare it to where it is with respect to the actual sphere that you were working on in the first place. Okay? So that's how we compute centroid. Notice that centroid is defined as a point, and you generally give that point in Cartesian coordinates, and you go about computing it whatever coordinates you want. I start off with Cartesian, but in the middle I said, hey, let's transform to polar to do the area integral, just because of the symmetry of the problem. So that depends on the problem that you have at hand, okay? Why do we care about centroid? Centroid is the geometric center of an object, okay? It's the geometric center of an object. So when I look, or when you look at me, right, you identify the center of me somehow. Your brain is doing all these calculations all the time, right? You know, I'm coming at you. Well, I is the center of me. And your eyes can only see my shape, right? And if you think of that for a physical problem, say a ship moving through water, right? Think about the forces that are acting on the ship. As a ship moves through the ocean, you have boundary forces acting on it because the water is rubbing on it, right? Or is pushing it, keeping it from moving forward, it has to go around it. There's viscosity. It's acting on the shape. But there's another force, there's another two forces acting on it, right? There's the force of gravity acting downward, and a buoyancy force that's restoring it, right? But the gravity, as we know from Newton's law, acts on the mass. It cares about where the mass is. The water cares about where the shape is. The gravity cares about where the mass is. So when those things are properly in balance, ships float very, very nicely. They move very, very nicely. When they're not properly in balance, you get ships that tip over. Okay? So if the center of mass and the centroid are not properly placed based on the forces that are acting on them, you can have everything tipping over. Right? You've seen that before. So how will we calculate the center of mass? Well, I guess I went slower than I expected. Was this too easy? It looks like everybody's like nodding. It's too easy for everybody. Going too slow. I hope you like that it was at 3/8. I hope that's like, oh, aha. It inspires you maybe to go calculate centroids of other objects. Where's your centroid? That's an essay. Ooh, that's a great essay question. Calculate your centroid. I wouldn't want my centroid and center of mass for me are all in that kind of old man's gut. So the only difference between centroid and center of mass is that center of mass is the mass-weighted center. Okay? So the center of mass is a physical. Okay, so let me say right now, the centroid is a geometric and therefore mathematical idea. But center of mass is a physical notion that requires more information about the object. Okay, and let's start with another. Let's go with another example. So let's imagine two cubes now. We're going to keep them at the same size. So this is two cubes, and I'm going to do my standard thing, which is I'm looking straight at it, so I don't have to try to draw 3D perspective on this board. Okay, two cubes, each of volume L cubed. Okay, so if you take a look at this, this is a cube that has side length L, L, and L. L by L by L. This is L over 2. This is negative L over 2. And I put them so that the centroid of this system is now shifted to the origin. The centroid is on the origin. Okay? So you go from x equals negative L over 2 to x equals positive L over 2. Those are the two centers of the individual cubes. Now let's do a very simple thing. This is air. This is full of air. And this is full of lead. Okay? So how do we define the center of mass? So the centroid, xc bar, is equal to 0 by construction. Okay. What is xm bar? Where that's the x component. This is the x component of the center of mass. So you see from here that I have given you more information. I have added a physical thing to this, which is one is lead and one is air. Okay? So you can go to Wikipedia or wherever you go to find your information about lead and air. I don't know what the density of lead is. I just used the word density. But let's say that mass of lead, the total mass of lead is 1,000 kilograms, and the mass of air is 1 gram. So a factor of 10 to the power of 6, a million times. I don't know if that's true. So we define the x component of the center of mass is equal to the x location of the air. And by that, I mean the center of this cube of air, where I'm considering it like a homogeneous medium. It's only air in there. Multiplied by the mass of the air plus the x component of the lead, that's the x center of the lead, multiplied by the mass of the lead. And you see here clearly we've got kilograms times meters in the numerator. And we must get a distance out of this averaging, so we must divide by kilograms. So what would you divide by? You would divide by the total mass that's in that system, in that joint system, which is the mass of the air plus the mass of the lead. And in this instance, this is 10 to the 6 times this, right? This is a million times this. So this is tiny. The mass of the air is tiny. This is negligible. The whole thing is just going to be the x location of the lead is the center of the lead, essentially, because I made such a great difference between the two. But that's not the essence of what I want to talk about right now. What I want you to realize is that I can imagine not just the mass of the air, but I can imagine what I need to think about is that there is air and there are other, it's not like just a discrete thing, air and lead, right? We can have alloys of different materials, lead and tin and zinc, right? We can have air included in that somehow, or water included in that. And what you see is that there is a notion that you can take a look at some complicated domain, say some D is a mixture of elements. And what we do is we imagine going in here and taking a piece. Take a small delta V, a small volume out of here. Measure the mass of the delta V volume, of the volume you cut out. How do we measure mass? You weigh it, and you divide by the gravitational constant, 9.8, or 10 meters per second squared. And when you measure the mass, you have, let me call this delta V1. This is the cut, this is, this is number 1. This is piece number 1. And this would be mass number 1. Now notice, everybody, if I have a big volume, I'm going to have more mass. If I have a smaller volume, I'm going to have less mass. If I have a smaller volume, I'm going to have less mass. The mass is basically proportional to the volume. As I decrease the volume, I decrease the mass. So instead of calling this M1, I'm going to call this delta M1 because it's the amount of mass that you cut out. And so we define this notion of density is equal to the amount of mass you cut out divided by the volume you cut out. And this has a well-defined value in the limit that delta V goes to 0. Think about it. I have a sense of mass. Just take water, for example. Just take a constant mass thing. You have water. I can measure the mass of a big jug of water, and then a smaller and smaller and smaller and smaller and smaller jug. As I decrease the volume that I'm measuring, I'm also decreasing the mass. But if I calculate this ratio for the big jug, for the smaller jug, for the teaspoon, for the eyedropper, this ratio, the amount of mass compared to the volume I'm measuring, is maintained in the limit that delta V goes to 0. This goes to a limit. And that limit is the density, okay? And in the book, they use delta. Little delta. Little delta denotes the density. I'm going to stop in 1 second, okay? Little delta of x, y, z denotes the mass density at any point in a domain, okay? In a domain. And I'm going to finish this off on Wednesday, but look what we're going to do. The numerator here, we're going to take the limit that m is small. We're going to divide delta m of the air divided by delta m of the volume multiplied by the volume. So I'm going to replace this with density times volume of each piece. Density times volume, density times volume. And the denominator will be density times volume, density times volume. And so we're going to see that if I did the same calculation that I did for centroid, but by putting the density in there, that delta, I will actually be calculating center of mass. And if I did the same calculation that I did for volume, but I multiplied by delta in there, the integral of delta with respect to volume is the total mass. And that's the subject of 15.6. That's what you guys are doing in 15.6. Okay? More on Wednesday.